Hi guys, this is Aryan Soni from Team Navid SGSITS Indore. Today I'm gonna show the optimization and structural validation of our brake pedal assembly, which our team GS Motorsports gonna use in their 2025 pedal assembly in 2025 vehicle for Supra SA 2025. So I'm here with the design team to structurally optimize these pedals for our vehicle pedal assembly. First, have our both pedal, accelerator pedal and brake pedal to optimize. So let's start with the accelerator pedal here. So let me partition the model for application of our boundary conditions. It should be of 5 mm top plate and then bottom cylinder for 3 mm. Yeah, it's good. Okay, now so our partitions has been set. Let me calculate the mass. It's 3.517 kgs, and my final goal to consider with consideration of both the pedal weights should be 1.5 kgs. Under 1.5 kgs, I have to put both the pedals under 1.5 kgs. So let us set our boundary conditions. So first I'm going to set the supports, and that will be cylindrical support. I'm going to apply for a constant force at the y direction of 35 Newton. So let me apply those. A constant force of 35 Newton in y direction and a constant pressure of 0.35 MPa in the normal of the phase. That will be 0.35 MPa. Yeah. Let me set my design space, which will be the partition opposite, or I can say the part of the model which we want to optimize. Like for our structural optimization, topology optimization, we have to set a particular space design part which we want to optimize, and it's a good practice to do not apply forces or boundary condition on that part. So let me start the simulation of our optimization simulation. More accurate, 6.4 mm. Yeah, it's okay. Accelerator pedal, accelerator pedal. So accurate. Let me see the load cases. Only there are 2 load cases. Yeah, okay. I'm gonna use here a single draw on this direction for opposite one in this plane with the opposite direction, and then I'm gonna use for symmetry. I'm gonna use the symmetric plane, this one, not the center one. Yeah. So let's perform and see what will be our outcomes. So this is our outcome. So this is our final, pre-final design. So we can consider here as we can clearly see there are 2 parallel plates joining the lower cylinder. We can clearly see the bottom cylinder is connected to the top rest plate, the 2 parallel plates. So by this observation, I'm gonna further aim the manufacturing of pedal through sheet metal manufacturing, and by bending of sheet metal, we are gonna manufacture this. So let's prepare our sheet metal processing design. We are ready here. So my goal is to make the accelerator part penetration work with the sheet metal and the cylinder, and then we are going to weld it with complete and with each other. There will be 2 welds over here, one here and one back till the point it possible, and same as here. So let's get started with our, and there's a top plate for our boundary condition applications of our boundary condition. I just added this. So let's start. So first let us set our design space, which is this one, and also material in previous one, that should be size 1080. Now so let's consider this weight is coming right now is 0.753. So I guess I should perform a structural analysis for its validations, whether there is any kind of issues. So let's start an analysis. First, let's set the boundary conditions. Let's have this cylindric supports here and pressure of 0.35 MPa. That's right. And then I need a force of 35 Newton in the direction of X, no, it's Y, that direction. And let's have okay, so let's quit it. And now we have our boundary conditions of our pedals are ready. So not just let me create more load cases. That's it. Now let's load cases, gravity, speed, accuracy, more accurate. Event size is okay. Load cases both are selected and now run. So this is our it's going on. So we have our iterations ready. This is our final first iteration analyze and simulation, and this is our complete for result envelope. This is our displacement. Let's go for vector of safety. It's coming around minimum 0.6 mm. That's away 6.1. That's coming at minimum. I guess I should not do that. It's coming to be a 0.6 mm. Let's separate it down and see. There are the minimum maximums are. I guess it will show me. So here the minimum vector of safety are coming 1.6.1, which is way more than we can consider it. So let's by this observation we can start our another optimization, that's a structural optimization once again, and structural optimization. So let's go there. First let me confirm the split draws, and for this one that this symmetry, let's create a symmetry for this. So we have our boundary conditions for structural optimization ready. For topology optimization we can just say that. So let's start pedal 1 now. Go. So it's on 25%, it's okay. For more accuracy, minimum it's 10 mm, it's okay I guess. And I have our load cases ready. Let me see. Yeah, they both are okay. And start. What to make a part design space? Oh, wait, instead the design space for it. This is our design space, by the way. And material, I guess it is selected. Okay, then run. Set now correctly running. We can see. Let's wait for the results. So our result came out to be these, like structure and topology simulations are results are this. So we how it has been attached, like we have these two ribbons like structure going on there, but okay. As we can see that the stress concentration were higher in bottom point, so they are not that they are not these. Okay, yeah, I can see it's being good. So let's add in structural optimization. We can just analyze it, and it can show us the results. So the analysis results are there, and its vector safety coming as 1.8, which is okay. And let's have our percentile yield. It's 54.33%. It's overall, it's okay. It's really nice. For 1 message stresses, it's 2065 plus 2. Okay, it's I can consider it as my final iteration, and I cannot perform one or more iterations over here. So this should be a final. It's looking really nice, no doubt. It's a great software to work on. It's a very easy and a very common nominal software. No hard issues and nothing that fit polynomials. This is our one of the design ready. By the way, these are the results for fit polynomials. I just started. It's looking really good. I play not these two results, because I think it should have a flat at the time of. Hey guys, we are once again back. This is our brake pedal, which we are going to, all the constraints of all the dimensions are fixed. Now we have to optimize this brake pedal for our design, our chassis, our car pedal assembly. So let's start it. Let me set its material to 100 and calculate the weight. It's coming right now 4.156 kgs, and it's a way much. And my final aim is to converge all the accelerator pedal and brake pedal weight to both total weight to be under 1.5 kgs. My goal was this. So let's start it. And our accelerator pedal came out to be around 0.4 kgs. I forgotten for that the weight consideration. So let's start it. And now Yeah, let me partition it. Geometry partitions both the boards of 3 mm, then a top plate to be around, I guess, 4 mm. It will be okay. And now just put it right in. This is our design space where we are going to optimize. So let me set the boundary conditions for this. Suppose once again we are going to have some supports that will be from here, and then our forces do the running supply over here. That will be in y direction, and it's 35 Newton, not it's around 85 newtons for a big pedal. And once again we have to consider a pressure, constant pressure on that will be one single only, and it's 0.35 knot. It's 0.618 ampere. That's all the calculations we have done. We have taken out all the calculations for our pedals, and consider one more force over here for the bottom. This one, when the maximum actuation of our brake pedal will be there, then there will be a restriction from the balance bar to our pedal and the pistons. So let's apply that force. That force should be of 85 Newton, I guess. No, it's around 22. It will be of 2. Let me see. It's around 2200 newtons. So, its direction is not okay. So it should be of x-axis. Yeah. Okay, it's okay. So our boundary conditions for our accelerator, our brake pedal is set. So let's have our boundary conditions set for our topology optimization. So I'm gonna shape control, and for shape control I'm gonna set it as once again a radial draw with a symmetric position, and or I can set a split draw on this axis, I guess, and perform it backwards. I can do it, I guess. It will be fine. So let's have a symmetry over this shape, and it will be only and only this one, not the. Okay, so our optimization. Let's start our optimization. So let's see. For more accurate, and it's okay. 25 maximum stiffness. Load cases. Let me consider the load cases. Different load cases. New load case support. And let's have the pressure here. Then let's run. Have a run. Run for more than so while it's running, so the results are here. These are the optimization, and it's pretty good, I guess. It's again showing the same path as our sheet metal manufacturing. We consider it as once again a process of sheet metal manufacturing. As we can see, there are split parallel plates, mostly parallel, not in these down spaces. So I can consider it a thickness of, I guess, 5 to 8 mm plates. It will be okay. 5 mm, it will be okay for 5 mm. And yeah, this is our first optimization of our brake pedal. So let's have a design ready according to the sheet metal manufacturing for a brake pedal. Also, we can see that we can manufacture it with our sheet metal manufacturing process. So let's start. Let me prepare once again a brake pedal geometry, and I will be there soon with you. Yeah, let me calculate the weight of it. It's 0.641 kgs, and I guess it's a pretty good. According to me, it's good. Let me prepare a model and see for what weight it comes. So this is our structure, our basic design of our sheet metal manufacturing. These two cylinders will be welded with our pedal, and let's. Oh, I have forgotten one thing to put here. There should be a plate for a boundary condition. For applications of a boundary condition, we cannot directly apply. For structural optimization, we cannot directly apply forces on design space. So let me make that real quick. Let's have it extruded for 4 mm. It's more than enough. Yeah, just set it. Okay, so finally our design is ready. So we have our two part 1. Let us make some partitions. That will be for base partition at 3 mm. Okay, this one 3 done. So now our design states. Let me set all the materials. at once as 1080, and let me also make it our design space. So this is the design, and let's start it. So first let me set the boundary condition, whatever I have here. Let me add a support over here, and then our forces to be 2200 newtons on the direction of x-axis. I guess it's okay. And now let us set our center force, our radial forces to 85 newton on the direction of phi. Yeah, let's set. And one more thing, let me set the pressure for the that will be applied by our driver's foot. Let me apply the pressure of 0.7 MPa. It's okay, nice, it's clear. So our boundary conditions are ready. Let's analyze this part and see how it performs. Let me see the load cases. Are they fully distributed? No, it's not. Let me create another one. Support, pressure. Okay, let's have an analyzation of how our design is performing. So it's running now. Let us see what will be the outputs. So our results are ready. These are the results. Let me go for result evaluation, and it's showing a minimum deflection of 0.8. Go for factor of safety. It's going to be 3.2, which is minimalistic, and it's on a cylinder rings. It's okay, no problem. We are gonna have weld over there, and let's percentage yield. It 30%. Okay, we can optimize it furthermore, but not that much. One assisted is okay, 62. It's okay. Show auto directions. Show this. So this is my panel, and actually we have the first one where I did it just show me a single flange. It's a mess up, I can say. So I performed multiple optimizations, and I got a study that after some optimization there are filled up space over there, but on previous ones it's so empty. So I can say this, these are the low stress areas. I can say that. No, sorry, why should I prepare this? So again I did analysis of this one. So many analysis and all these, everything I've done each and every time. But the final one which I did was this. Yeah, it's this. So it came out to be was 1.7, 1.8, which is okay. So it's okay, we can consider it. Then the percent of yield, it was 60%, and I can say it's pretty good. I have seen a factor of safety, I can say 1 stresses, and maximum it came out to be 2.58. And as I can see it's not that much stress area, it's just area. It's not showing that the heavy loads or stresses. Let me do for result evaluation. Yeah, so it's not showing that much stresses, like it's 0.1, 0.9. Then too there are the fill stresses. So let me prepare a geometry where I can combine these both alterations at the same time. So okay, so this was the final geometry which we can say it's ready. Now let me prepare a dominant geometry for our accelerator pedal. Oh, sorry, RX bar brake pedal to be final one. So I can consider it as a pretty good one. And let me hide this so I can see. Yeah, so this will be my final design, and I will be considering final output. So this was this is all the simulations and iterations which I have done over our great software and ANSYS Inspire. I'm saying ANSYS on our Altier Inspire software, and it was great to perform analysis and simulations over there. It's a really great for topology optimization. It's really structural optimization is like butter smooth. Everything we have to set, it's pretty good user interface and a really friendly. I have learned it pretty quick, and it's showing results that are way acceptable. Like it's way better than any other software which I have performed. Really, it's my honest opinion that it is a way easier and a way user friendly software than any other software. I have performed simulation in many more softwares, other softwares, but this is, I can say this is a really good combination of each and every type of optimization so on we can perform. Like there are many more implementation, modeling, motion, fluids, manufacturing. These all is a very compact and a really good software, I guess. So yeah, thanks for watching. This is my final. Let me show you the final both designs of. Let me prepare final designs of our both pedals, and let me show you those. Yeah, so these are both of our pedals ready here. Now we can say the weights are coming to 1.25 to 41 kgs, and it's under 1.5 kgs, which was my goal. And both the pedals are like really good, and I have validated these both pedals, and these are now will be going to attach to our FSAE car for our running, for car to be running. This I can say this, the Altier Inspire is a really good software. I have loved it. And thanks for watching. These are our final designs. Thank you.